Today we're going to talk about scientific processes. In the past, when we've talked about scientific method in your previous science classes, we've always talked about the scientific method as a list. You first do this step, then you do that step, and then next after that comes the following step. That's not the reality of how the scientific method works when you're a working scientist. In reality, it is a circular, more circular and iterative. You can pop in and out of the scientific method at any time, and we're going to discuss that a little bit today. But before we do that, let's talk about what chemistry is. Chemistry is everything you see, everything you touch, everything you feel, everything that you encounter has to do with chemistry. Chemistry, the definition of chemistry that we'll use in this class is it's the study of the composition of matter and the changes that matter undergoes. So that means we're studying what things are made of and how they change. And there are many everyday applications to chemistry. You've got manufacturing materials, how you put things together in a way that's efficient and has small amounts of waste. That has to do with chemistry. The energy that is made, whether to make electricity from fossil fuels or from solar energy, or the energy you use to fuel your body, or the energy to fuel your car, that sort of stuff is all chemistry of some sort. Medicine and biotechnology. All the medicines you take were made in a lab at one point. They were developed in a lab, and then they were processed in a manufacturing location. Agriculture, you fertilize your crops. That's all chemistry. And the environment, the air you breathe is lots of different chemicals in the air, and they all react in different ways. There are 5 main branches of chemistry. Organic chemistry is the chemistry that, when you think of a stereotypical chemist with the white lab coat and the hair sticking up and things like that, that's usually an organic chemist. An organic chemist is someone who studies anything that has carbon. Okay? Anything that has carbon. There's so many things that have carbon. There's a whole branch of chemistry that involve it. Then you have inorganic chemistry that focuses on things that don't have carbon. So mostly non-living things, since things with carbon are living. Most things with carbon are living. And this class that you're taking is mostly inorganic chemistry. But if you do go onto AP Chem, after AP Chem, you can take an organic chemistry. You can take organic chemistry here with Dr. First. A nice class. They'll get you ahead for your sophomore year in college. Then you have your analytical chemistry. This is the chemistry that studies how your chemicals are put together, studies the composition of substances. So a forensic chemist, typically an analytical chemist. They can take an unknown substance, a white powder, and tell you what it is because they're analyzing the composition, how it's composed. When blood is taken from your arm, an analytical chemist can see how much of the medication that they gave you is actually in your blood. Things like that. What are your white blood cells? White blood count? All that is chemistry. Then that brings you to PChem, physical chemistry. That's the study of behaviors of chemicals, how they behave down to the atom. What does each individual atom do? Is it rotating? Is it vibrating? Is it stretching? And this is described mostly by mathematical equations. It's the marriage between physics and chemistry. Physical chemistry is the marriage between physics and chemistry. The physicists call this branch chemical physics. We call it physical chemistry, where quantum mechanics lives. Then you have biochemistry, which is the marriage between biology and chemistry, and that is the study of all living organisms. So anything that is living is biochemistry. And anything that has to do with living organisms. So none of these branches live in a vacuum. They all overlap. Because, for instance, you can't study biochemistry, the chemistry of living organisms, without knowing organic chemistry, which is the study of carbon, since living organisms are made up of carbon. You can't study analytical chemistry, or you can't say biochemistry without analytical chemistry. So they do not work in a vacuum. Okay, so now we get to the scientific method. So again, I'm giving it to you as steps. However, just know these steps, you can jump in and out of the steps at any point. You can go back and revisit a step because science is iterative. You're always making new discoveries and making tweaks. But for the sake of this presentation, we're going to talk about it in terms of steps. So the first thing that happens for the scientific method is that you observe something. That means you're out and about and you see something and you say, huh, look at that. You observe it. You're like, huh, isn't that interesting? And you observe it and you say, I wonder why that happened. And you state the problem. What is it that you observed that you now want to study? What is the problem you now want to study? And then because we need to be able to direct our studies, we don't want to just be like out with no direction. We form a hypothesis. And a hypothesis says, this thing I want to study, I think this is what is going on. And it's an educated guess. And it has to be something that is testable, something that you can measure in a lab and test it. That means you can't have any morals or value of judgment, no opinions. It has to be something that is testable, that is will give you the same results every single time, testable and repeatable. Okay, so you walk around, huh, isn't that interesting? I wonder why this happened. So you observe something, you state the problem. Then you make an educated guess. You direct your research. And at this point, since you now know what you want to test, you set up an experiment. You design your experiment. And this takes a long time because you have to design an experiment that is going to answer the question, answer your hypothesis, which does not need to be a question. It can be a question, an if-then question, or an if-then statement, but it does not have to be. I know you've been taught that previously, but now that we're a little more mature in our science, you can make it a statement. Okay, so you set up your experiment. It takes a long time because you have to take so many things into consideration, including safety. They need to be considered and planned for, and you need to have contingency plans for everything. Okay, so you went, huh, isn't that interesting? You observed something, you stated the problem, you formed a hypothesis to lead your thinking, you set up, you designed your procedures, you experiment, and now comes the next step. So here it's written as 2 steps. However, it's 1 step. However, I like to think of it as 2 steps. The first step is record your data. That is your observations. That is raw data, no interpretation. A lot of times that data, you put it in the table or something like that, but you're recording what you see. Like you're recording what you see, nothing else. No inferences. You're not making any guesses of what the reason these things happened. That comes next, and that's in the analysis or the results of your data. Okay, and there you're going to make inferences. You're going to make predictions based on the information that is provided, based on what you saw. That you're going to plot up your data. If you have numbers, you can put them in a graph and look at trends. And what do those trends mean? Are things correlated? Are they anti-correlated? What is there an equation that can describe the relationship between these things? And once you've done that, you can draw your conclusion and kind of wrap things up. Now, let's say you've set up your experiment and you've run your experiment and you've recorded your data, and then your hypothesis is not correct. That's okay. You address that. Or you've done your experiment, you record your data, and you realize that the way you set up your experiment did not answer the question that you were asking. It did not answer your hypothesis. So you have to go back and either see what it was answering or go and form a new hypothesis or make a new experiment design. In other words, this thing is iterative. You can jump in and out of it. It's not step 1, step 2, step 3. It could be step 1, step 2, step 3, step 4, step 5, back to step 4, back to step 5, back to step 3, and just keep changing it like that as needed. Okay, your observations. When we talked about it before, when I said it's its own step, it is raw data. You're just recording what you saw. You're not making any predictions on that. So for instance, if you have a block of ice and you have a block of ice, you apply heat. You do not say that the ice melted to form liquid water. You don't say that because you don't know that. All your observations can say is my ice formed a clear liquid. Then in your analysis of your data, you can make that inference. You can say my ice melted and formed water. But when you're taking your observations, you just you write what you saw. A clear liquid is formed. Okay. Your hypothesis again is a proposed explanation for what's observed. It's an educated guess, and guesses can be wrong. Guesses can be wrong, and that's okay. Okay, again, to talk about hypothesis, it has to be testable. It has to be measurable. No opinions. So let's look at this hypothesis statement here. Clouds are more beautiful on a winter day than on a summer day. This is a poor hypothesis. It's not a poor hypothesis because it isn't a question. It doesn't have to be a question. It's a poor hypothesis because this is an opinion. Opinions cannot be tested and proved. Everyone has different opinions. You may think your clouds are more beautiful on a summer day. I might think they're more beautiful on a winter day. That cannot be proved. You can observe the clouds. You can make comparisons. You can say the clouds in the summer are puffier and the clouds in the winter are wispier, but those are not answering that hypothesis. And the reason this hypothesis is bad because it is not testable or measurable. There's no way to measure or test an opinion. Again, if the hypothesis doesn't fit, you make a new hypothesis based on observations, or you make an inference on what the data could be showing. So maybe your hypothesis isn't right, but what does it mean? What does your data mean? Right? Your hypothesis is just to focus your research. If when you focus your research, your hypothesis is completely wrong, that's okay. You just adjust. Science is about adjustment. Okay, which then leads us to scientific theory. You've got your hypothesis. That is an educated guess. You're running an experiment. Then you get to scientific theory, like the theory of evolution. And theory are based on experimental data. Okay, a theory is not a guess. It is based on actual data. And it's been confirmed by many, many repeated experiments by many different people, many different experimental designs, and all coming with the same results. Okay, it is a theory, but it is modified as new information is gathered. So, like the theory of evolution, every year they're finding a little bit more, and so they modify it and they tweak it. And so it's a theory. It's well established a theory. Most scientists believe in evolution and believe it's something that occurs because the data supports that. But we get more and more data, so we keep changing it just a little bit to refine it. We're refining the theory, but it's multiple experiments leading to the same thing. Okay, so once a theory has been around for a long time, it can be promoted to a scientific law. This is what a scientific law is, what a theory becomes when it gets promoted. Theories become laws when nothing has changed for hundreds of years, like the law of gravity. That law of gravity has been defined by the same mathematical equation for hundreds of years. It has not changed at all in hundreds of years. It's very hard to become a law. You have to stand the test of time. So it's kind of set in stone. However, because science is always progressing and our technology gets better, our instrumentation gets better, our scientific knowledge and thinking gets more mature, sometimes something that stood a test of time and has become a law, new information comes out and it might change that law just slightly, just tweak it. As soon as it gets changed, it is now demoted again to be a theory. And then it has to go through hundreds of years of not changing before it can become a law again. So to recap, hypothesis is an educated guess. Scientific theory is based on experimental data. It's been tested by multiple experiments and is modified as needed. A scientific law is a theory that has become is stable for hundreds of years and has not changed in a long time. But it still can be changed. And once it is changed, it is demoted. Okay, which then brings us to our variables. I'm skipping the engagement portions right now. You can go back and do this on the student paced Nearpod. So when you design an experiment, you need to take into consideration your variables. Okay, so we have three types of variables we talked about in this class. We're going to start with our dependent variable. Okay, dependent variable is the responding variable, the variable that responds to a change. That is the thing, that is the observation you are making. Okay, what happens? What is the result of something you did? And this is usually plotted on the y-axis. So we have an acronym for you. DRY. DRY stands for dependent variable, responding, y-axis. So it's the variable that responds to an action. It is the result of something that occurred. Result to something, some change that was put on it and plotted on the y-axis. Then that brings you to the independent variable. Independent variable is what's called the manipulated variable. It is the one that you are changing. It is the thing that you change. You change, and then there's a response to that change. That response is your dependent variable, but the manipulated variable is the independent one, the thing you change. And that is usually plotted on the x-axis. We plot things along on xy graphs, scatter plots, or line graphs. So we have an acronym for this as well. It is called MIX, manipulated, independent, plotted on the x-axis. Thing you manipulate. Okay? So when you set up your scientific method, you also need to have a controlled experiment, okay, in order to test your hypothesis. And the reason you do this is so that you're confident that the manipulation, the independent variable that you put towards something is the cause of your dependent response. Okay? You need to be confident that what you did to manipulate the situation causes the response, and not that the response is caused by some other factor. So you set up a controlled experiment, and you're going to have two groups. You're going to have a control group. That's where all variables are constant and the same. Nothing changes. And then you have an experimental group, and that's the group that receives the independent variable. So if you have an experiment where, as I spoke in class, where you've got some students and you're pulling on their arm, so you've got let's say four students. You have two students in the control group and two students in the experimental group. Okay, the two students in the experimental group, I go and I grab their arm and I pull on them. So that is the independent variable. I'm going to pull, that's what I'm manipulating, pulling on the student. And the response to me pulling them is the distance that they moved due to my pull. So the independent variable is the pulling, the response is the movement. Okay? The control groups would not get any pull, and we'd see if they moved. If they moved, then the fact that the experimental group moved had nothing to do with what I did. It just had to do with the environment. Okay? There are three types of variables that we talk about here. We already talked about what the independent variable is. That's the variable that changes by the experimenter in a group. You've got the dependent variable. That's the variable that changes as response. Changes as a result of the independent variable. It's the response. And then you have your control variables. That means everything else stays the same because you're only going to test one variable at a time. Okay? Everything else stays the same. So let's do an example. Let's say that we want to figure out what is the fastest route to walk home from school. So we're going to try several different routes and we're going to time it. See which is the fastest way to get home. Okay, so let's say one route is walking down the street, around the corner, and down the next street, and you get home. That's one route, route one. And you time that. You see how long does it take you to do that. Okay. The second route, would be maybe jumping over a couple fences because it's a more direct route, and you time yourself there as well. You see how long that's going to take. And then the third route might be swimming across a pond to get the pond that's near your house to get there from Ridge Point. And that's a third route. So you're testing 3 different routes. You are changing the routes and you're testing the time it takes to do each of those routes. And because you only care how fast it takes you to get home, you're going to be doing all the routes. Nobody else's. Okay? And in this situation, the independent variable is that varying route. Those 3 different routes. Those are the changes that you are making. You are making a change in your route. That's your independent variable. How long each route takes, that is the dependent variable. And the fact that the fact that only one person does the walking or does the route is the control variable. Now, if you wanted to find out how fast somebody else does it, then you would test them separately. That would be a second experiment. And then you would test a third person and a fourth person. Then you can put all that data together, but you do one at a time. One at a time. It's important to test them one at a time. All right, this is one of the questions that was on the engagement, but we're going to talk about it here because I think it's important. So, because this is actually a science, it's a science example as opposed to a walking example. So here it says, a medical researcher hypothesizes that a newly developed medication can reduce high blood pressure. Which of these is most likely to be the independent variable in a study involving this medication? Okay, so we're trying to find how medicine affects blood pressure. How medicine affects blood pressure. Your independent variable, the thing that you are changing, that you are manipulating, is going to be that medicine. You are going to give medication to patients. Then you're going to watch to see what happens to the blood pressure. That is your dependent variable. The medication you give is the independent. That's the change you made. No medication versus medication. You made a change from no medication to medication. Okay? And then you check the blood pressure. You check the blood pressure with no medication. That's your control experiment, right? And then you check the blood pressure with medication. And you see if it reduces that blood pressure. Okay? Now, when you get to measurements, you can make 2 types of measurements, 2 types of observations. You can make what are called qualitative measurements, and you can make quantitative measurements. Qualitative measurements are descriptive. They are words, only words. You can say, this is hot, this is cold, this is heavy, this is light, this is big, this is blue, this is furry. Those are all descriptive observations. Okay? You can also make quantitative measurements. Okay? Observations that are made with a measuring instrument, and they include both a number and a unit. For instance, you can measure something with a ruler, and you would say this was 2.8 centimeters. A number, 2.8, and it's a unit, centimeters. You can weigh something, and you'd say it is 25 kilograms. You can take the temperature of something. You would say it is 13.5 degrees Celsius, for instance, a number and a unit. Quantitative measurements are better than qualitative measurements because there is no question. So let's go back to those qualitative measurements. We've got one of the qualitative measurements is hot. Instead of saying this is hot, a better measurement would be take the temperature. Change that qualitative measurement into a quantitative measurement by taking the temperature. Instead of saying it's hot, say it's 44 degrees Celsius. Instead of saying it's cold, say it's 2 degrees Celsius. Instead of saying it's heavy, weigh it. Okay? Now, a way to remember which is qualitative and which is quantitative. Quantitative has the word quantity in it. So it has a number. Quantity is a number and a word. Qualitative is just descriptive. Just descriptive. Quantitative measurements are better than qualitative. We will make observations that are qualitative in this class when we do a couple labs, and you'll see why they're not good observations. You'll spend time saying, is this ruby red or fire truck red? Because it's going to be hard to make those sort of distinctions. Okay. So in that case, it's best to like take a picture or have colored pencils to try to get those colors exact on your lab report. You can actually have a comparison. Okay, tools for measurement. So when you do a measurement and a measurement, you need to use the appropriate measurement tool for the situation. You have to know the appropriate measurement tool for the situation. So if I say you need to stir this for 30 seconds, then I need you to use a clock or a stopwatch to measure time. I don't want you to count to 30 because that is not repeatable, and you counting to 30 might be different than me counting to 30. You need to use the appropriate tool for the situation. If I need you to have something that weighs a certain amount, then you need to use a balance to weigh it. We don't say this is about, no, you weigh it. If I need volume, then you use the proper tool for volume. If you need volume very, very precise, you would use something called a pipette. You need a little less, I guess I should say not precise, accurate, a little less accurate. You would use a graduated cylinder or a beaker. So you must use the proper measurement tool for the situation. Okay, when we talk about units, there are many, many units you can use. Meters, kilometers, liters, things like that. But there are some standardized units. They're called SI units, which are used across the world. So when we are talking about SI units, this is something that pre-AP needs to memorize, not on level. But when we're talking about SI units, you need to know them. So if I ask you for a measurement of length in SI units, I need you to give it to me in meters. If I don't ask for it in SI units, then you give it to me in the unit that is most appropriate for the situation. If I specify SI units, you must give me that measurement in meters. If I specify SI units for mass, then you must give it to me in kilograms. If I don't specify it in mass, if I don't specify SI units, then you give it to me in the appropriate unit for the situation. Always metric. We do not use pounds in this class. If I ask for time in SI units, you give it to me in seconds. If I ask for temperature in SI units, you give it to me in Kelvin. We do not use Fahrenheit in this class at all. We use Kelvin or Celsius. And because we're in chemistry, we use a unit called mole, not a mole. And that's 6.02 times 10 to the 23. And we'll talk about that in a few weeks. But if I ask for an amount of molecule, an amount of carbon dioxide, then you're going to give it to me in moles if I ask for it in SI units. Okay. Which then brings us to our limits of measurement. We have 3 main limits of measurement. We're going to talk about 2 here, and we'll talk about the other one in a little later in this class. So the first 2 things, the first 2 limits of measurement we talk about are accuracy and precision. And this is how they're defined in science. They may be defined a little differently in engineering, but this is how they're defined in science. So we're going to start off with accuracy. Accuracy is how close a measured value is to a true or an accepted value. That means how correct are you? If you know what you're trying to aim for, did you get it? How correct are you? And accuracy is determined by just one measurement. If you got the right measurement one time, just one time, then you were accurate. You are accurate. Just like if you're playing darts and you hit the bullseye once, doesn't matter that you hit the wall 16 times. and never even hit the board. If you hit the bullseye one time, you won the game. You were accurate. All it takes is once. And your accuracy depends on how good the measuring device is. And how good the measuring device is. How good can you measure your volume in a graduate cylinder is much better, has better accuracy than, let's say, a beaker to measure volume. So your accuracy depends on the quality of the measuring device. So let's look at this density of water. The density of water is 1.00 grams per milliliter. That means if you have 1 milliliter of water, it's going to weigh exactly 1.00 grams. That's what density means. Or if you have exactly 1.00 grams of water, it's going to be 1 mil water. Okay, so if you look at these lab measurements, somebody's trying to come up with the density of water. And here, did not hit the 1, did not hit the 1.00, did not hit the 1.00. Oh, right here, 1.00. This person doing this measurement hit the right density one time. They are accurate. They hit it one time. They are accurate. Okay. So now let's look at some examples here. There's a book, and it's got a true length of exactly 17.0 centimeters. It's well known how big this book is. So Susan comes along and tries to measure the book. And she measures 17.0 centimeters, 16.0 centimeters, 18.0 centimeters, and 15.0 centimeters. And Amy comes around and she measures 15.5, 15.0, 15.2, and 15.3 centimeters. So let's start with Susan. Susan's not very good measurer because she's all over the place. She's measuring the same book 4 times and she comes up with different values every single time. However, she did hit 17 centimeters one time, so she is accurate. Doesn't matter, all the other ones are off. She is accurate. Amy, however, she seems like she's pretty consistent when she measures. She's always measuring around the same, but it's nowhere near the actual 17 centimeters. So she is not accurate. Only Susan is. Which then brings us to precision. So remember, accuracy, you only need one measurement to be right to be accurate. Precision is how close a series of measurements are to one another. How close a series of measurements are to one another. That means that you're going to need multiple measurements. And your precision, again, your precision is determined by more than one measurement. And your precision depends on the skill of the person measuring. The skill of the person measuring. An analytical chemist who's looking at quantities and looking at the composition of things has to be a very precise chemist. An organic chemist does not, but an analytical chemist needs to be very precise. So an analytical chemist has very good lab skills. Okay? It depends on the skill of the person. Remember, accuracy depends on the measuring device, the instrument, the glassware. The precision depends on the person. So let's go back to the density of water. If you look here, here's somebody who's trying to find the density of water. And they are at 0.89, 0.87, 0.89, 0.88, 0.88. Nowhere near that 1 gram per milliliter. They are not precise. However, they are not accurate. However, they are very precise. Very precise. Those numbers are all very close to each other. Precision is how close you are to each other. So let's go back and look at Amy and Susan again. Remember, Susan was accurate because she hit 17. Amy never hit 17, so she was not accurate. So let's look at Susan. Is Susan precise? No, her numbers are all over the place. Precise is how close the measurements are to each other. So Susan is accurate, but she is not precise. Amy, however, all her measurements are very close together. So she is precise, but she's not accurate. So accuracy is how correct you are. Precision is how consistent you are. How correct you are versus how consistent. So one way to remember it is accurate. Second letter in accurate is C. C for correct. Precision. Second letter of precision is R. R for reproducible. Correct and reproducible. Precision requires many measurements, so you can have reproducibility. Accuracy only needs one measurement to be correct. Okay, so let's talk about these bullseyes. We want to find out whether these are accurate, precise, neither, or both. Let's start with the easy one. Let's start with D. D, you're hitting the bullseye. So D is accurate because you're hitting the bullseye. But if you notice, all of them are hitting the bullseye. This person is a really good dart player. They're both accurate and precise. That is accurate and precise. Okay, let's look at B. B, that's the next easiest one. B is nowhere near the bullseye, so they're not accurate. These guys are all close to each other, so they are precise. So B is not accurate, but it is precise. Okay, let's go to A. That's the next easiest. Is it accurate or precise? Neither or both. Well, you hit the bullseye once, kind of on the edge, but let's pretend that's the bullseye. Let's pretend it still counts as a bullseye because it's still within the red circle. This is accurate. But look how spread out all these guys are. They're not accurate at all. I mean, they're not precise at all. A is only accurate. So D, accurate and precise. B, only precise. A, only accurate. And C has accurate. And so this right here becomes a judgment call. These are all pretty close together. However, you got some in white and some in red. So this is just a judgment call. And this would really depend on how you're measuring. What are your parameters? What the significance is of your measuring. So that has to do with your what's called your significant figures, your significance of your measuring device. And we will talk about that on Monday and Tuesday of this week. Okay? So in a lab, you want to be accurate and you want to be precise. You want to be accurate and precise. But if you could only choose one, which would it be? Would you prefer to be accurate or would you prefer to be precise? And the answer is, if you had to choose one, you would prefer to be precise because you can correct for precision. You can correct for not being able to throw the darts at the bullseye if you're always hitting the same spot. You can correct where you're aiming at. But if you are not accurate, there's nothing you can do to correct it. Remember, the accuracy depends on the measuring device. You can't do any better than the beaker you're using or the graduated cylinder you're using. You can't correct for bad manufacturing. You can't correct for not good instrumentation, but you can correct for your precision. You can adjust things. Okay, if there's any questions, please let me know. I've also posted in Schoology a folder within the scientific processes folder. I posted a folder, which I'll do in every unit, that's called online resources, and there are YouTube videos describing these things individually as well. Thank you.